Hello again. Our topic for today is an arithmetic variant of Ramsey theory. We're going to be looking at the van der Waerden numbers. So let me briefly teleport you into my office here, and I pulled off the shelf this here abacus. Now, I'm not much of a musician, so I don't really know how to play this thing, but I'm told it's one of the early symbols of arithmetic, and so I thought it was fitting for today. And we may even see something in what we study today that is a little bit reminiscent of this abacus. Okay, let's get going and dive right in. First, we'll define a k-term arithmetic progression. Now, you've probably seen this before. This is just a sequence of k integers of the form a, a plus d, a plus 2d, up to a plus k minus 1d. So there are k integers here that are equally spaced, with the difference between successive ones being the integer d. Our theorem for today that we're going to look at is due to van der Waerden from 1927. It says that if r and k are given positive integers, then for sufficiently large n, any r coloring of the integers from 1 to n contains a monochromatic k-term arithmetic progression. The least such integer n for which this guarantee kicks in is called the van der Waerden number, w of r comma k. So again, for n up to 1 less than this w of r comma k, there is an r coloring of the integers 1, 2 up to n, so that there are no k-term arithmetic progressions all painted with the same color. But at the van der Waerden number or beyond, there is a guarantee that no matter how we paint the integers from 1 up to n, there will be a k-term arithmetic progression, all of whose integers are the same color. Okay, let's look at some easy facts. I've kept the definition of w of r comma k here for reference. First, very trivial fact, w of r comma 1 is equal to 1. Well, of course, if we just have one element, then no matter how we paint it, we have a one-term arithmetic progression of that color. Now let's suppose we have n equal to r plus 1, and we're looking for a two-term arithmetic progression when we r color. Well, by the pigeonhole principle, if we only use r colors on r plus 1 or more integers, well then some two are going to have the same color, and any two integers form a two-term arithmetic progression. They will have the same color, and so we'll get the conclusion we want. When n is equal to only r, if we paint everything differently, well, we don't get any two-term monochromatic APs. Okay, now let's let r equal to 1, so we only have one color. Well, very trivial again. If we only have one color, we paint k or more integers, we get a k-term monochromatic arithmetic progression. If we have fewer, we don't get the KAP, but k or more, and we're guaranteed it. So these are some easy facts, just to get our bearings for what w of r comma k is doing. Okay, let's see a slightly more interesting example. We're going to be studying w of 2 comma 3 here. We're going to be showing an upper bound of 9 on this van der Waerden number, and later we'll see a matching lower bound for it. But for the moment, let's just prove that if we paint these 9 integers from 1 to 9 with two colors, I'll be using red and blue, and I'm sorry for anyone who has trouble seeing these colors, but they're sort of standard, and I had a hard time deciding what colors would show up best. But hopefully the explanation will make some sense. Okay, we'd like to show that no matter how we paint these 9 integers, we're going to be guaranteed a monochromatic three-term arithmetic progression. That is 3 equally spaced numbers all of the same color. Okay, consider the middle integer 5. We may as well assume it's colored red, say. Okay, now the analysis is going to be divided into two cases according to how 1 and 9 are colored. They can't both be red, Or if they are, we get a three-term arithmetic progression that's all red, 1, 5, and 9. So following this kind of logic, throughout the sort of analysis of this van der Waerden number, we're going to keep forcing through the coloring, assuming we don't have a monochromatic 3AP. Okay, first, in the top case, we have 1 colored blue, 5 red, and 9 blue. Consider 3 and 7. They can't both be red, for then 3, 5, and 7 would be a red 3AP. So one of them is blue, and we may as well assume by symmetry that 3 is painted blue. Now, under the assumption of no monochromatic 3AP, we're going to be able to push through this coloring to a contradiction. The integer 2, being between 1 and 3, has to be red now. Now, if we look at 2, 5, 8, since 2 and 5 are red, it means 8 must be blue. And now 8 and 9, both being blue, we must have 7 red. And now we have a contradiction because 6 can't be painted anything. It's between two red numbers 5 and 7. It's also equally between the blue numbers 3 and 9. Okay, let's look at the second case. Here we've assumed one of 1 and 9 is blue and 1 is red. Without loss of generality, let's say 1 is blue and 9 is red. Well, now you probably see where we're going with this. We're going to start forcing through the coloring, assuming no monochromatic 3AP. First, 7 must be blue because it's between 5 and 9. Now, we get from 1, 4, 7, 4 must be red. And now, from 4 and 5 being red, we must have 6 blue. And 6 and 7 blue force 8 to be red. And now, from 2, 5, 8, we see that 2 is blue. And again, we have a problem. We can't paint 3 with anything. So altogether, assuming no monochromatic 3AP in both cases led to a contradiction. This establishes the upper bound of 9 on W of 2, 3. Now, for the lower bound, we'll see a strict lower bound of 8 here, and it's simply from this painting of the integers from 1 to 8. 1 and 2 are blue, 3 and 4 are red, 5 and 6 are blue again, and 7 and 8 are red again. It's simple to check that there are no three-term arithmetic progressions all of the same color. Okay, now let's turn to a sketch of the proof of van der Waerden's theorem. Now this is going to be very high level, won't get into a lot of details, but one thing that will be helpful to see in our look at this proof is it will be helpful to think of not just an arithmetic progression where we have a single difference d, but you can think of a two-dimensional or higher dimensional arithmetic progression where we have blocks of arithmetic progressions that repeat, them being equally spaced. And so I'll informally call this a higher dimensional AP. The proof works by an induction on k, the length of the AP we're seeking. Let's suppose the van der Waerden numbers W of r, comma k minus 1 exist for all r, that is all numbers of colors, and some integer k at least 3. Now I'm very sorry to do this to you, but we're going to define a crazy sequence of numbers. We're going to start with n sub 0 equal to 1. That seems innocent enough. But now, from one term to the next, the definition is shocking. We're going to let n sub t be twice the van der Waerden number, where the number of colors is r to the n0, n1 up to n sub t minus 1, the product of all the previous ones, comma k minus 1, using the induction hypothesis. But where the number of colors is astronomical. Okay, we're going to let n be the product n1, n2 up to n sub r. And we're going to imagine that the set of integers from 1 to n has been arranged into an r-dimensional brick with side lengths n sub I. These are the factors of n. Now we're going to show that in the integers from 1 to n, using this brick, we'll see that there is necessarily a KAP, all of the same color. Now by the way we chose n sub r, there exist k minus 1 equally spaced and identically colored blocks of size n over n sub r. That's the rest of the brick, which is size n1, n2 up to n sub r minus 1. Now that's because enough colors, namely r to the product n0, n1 up to n sub r minus 1, or r to the n over n sub r, enough colors have been used on the blocks to encode each possible sequence of r colorings, of which there are that many, as its own color. So we'll re-encode sequences of colorings that occur in the blocks as entirely new colors. Now, moreover, for a technical detail, it's helpful to assume that the k-1 blocks occur in the first half of the sequence using the factor 2 in our recursive definition of n sub t. Alright, now let's look inside each of these blocks and we'll apply a similar reasoning. So by chasing through the definitions of these n sub t parameters, we construct an r-dimensional arithmetic progression with k-1 terms in each so-called direction. And this is monochromatic. Let's assume all of these numbers are painted color 1. We'll see an illustration of this in a moment. Now, we claim that this forces a monochromatic k-term AP. If we were try to extend the coloring, we would choose a new color, say 2, in one direction. And so we'd have a r-1 dimensional AP that's color 2. In the next direction, we extend and get an r-2 dimensional AP of a new color, say 3. And this will inevitably lead to a contradiction because we'll locate eventually an integer which cannot be colored with any of the r colors. I think it would be helpful to see an illustration of the proof. Here we're going to suppose k equals 4 so that we're trying to avoid monochromatic 4-term arithmetic progressions. Have a look at the 9 integers that have been colored red. It may be helpful to think of them as the digits 1 to 9 on a telephone keypad, so that they're arranged in a way that we have horizontal, vertical, and diagonal 3-term arithmetic progressions. Looking in the horizontal direction, to avoid a red 4AP, we have to have the 4th point in each row indicated here a different color other than red. And moreover, they're all the same color, say blue as indicated here, because we've assumed that each of these k-1 blocks have all been identically colored. This comes from the astronomical number of colors we used in our induction hypothesis. Now, if we look at the point that's indicated as green, this integer is the tail of a 4AP from the vertical line, which starts with 3 blue integers, and also the diagonal line, which starts with 3 red integers. So this has to have yet another color. In general, we continue this way, forcing new colors to occur using higher dimensional arithmetic progressions. Now actually, if you write down a rigorous definition of a d-dimensional arithmetic progression, the proof actually isn't so bad to write out in a little bit more formal details, but the main point here was just to get an idea of the proof. Okay, so as for upper bounds, Tim Gowers has shown a general upper bound on w of rk, which is this tower of exponents shown 2 to the 2 to the r to the 2 to the 2 to the k plus 9. Now, although that looks like a horrifically large number in general, it's actually quite impressive that the tower of exponents here is limited to a bounded size, not depending on r or k. If you were to analyze the proof we just saw, it's not good enough to get a bound that's quite so small. Some specific known values are w of 2, 3 equal to 9, we saw that earlier, and w of 3, 3 equals 27. So here we have 3 colors trying to avoid a monochromatic 3 AP. So much like in our example, except we have a third color. That requires 27 for the guarantee to kick in that a 3-term monochromatic AP must exist. If instead we have 2 colors and we're looking for 4 APs, then w of 2, 4 in that case is 35. Alright, let's wrap up our treatment of the van der Waerden numbers with a naive lower bound. This is not a very good bound, but it's illustrative of the probabilistic technique, which, remember, we also used this to prove a lower bound on the 2-color Ramsey numbers. Okay, the bound here says that for an integer k greater than 1, the van der Waerden number w of r comma k is strictly greater than r to the exponent k minus 1 over 2. So that is, if we let n be the right-hand side, this r to the k minus 1 over 2, then the bound is saying that there is a way to paint the integers from 1 to n with r colors so as to avoid a monochromatic KAP. We'll do this by taking account of all the bad colorings that do have a monochromatic KAP and showing that there's at least one left over. So in the first n positive integers, we can estimate the number of k-term APs. It's at most n squared over k, since we have at most n choices for a starting term, and then at most n over k choices for a distance between successive terms. Now the actual count is a little bit better than this, but this estimate is enough for our purposes. Now if we paint the integers from 1 up to n with r colors, the probability that a given KAP is monochromatic is r, choices for a color, divided by r to the k, the total number of ways to paint that KAP. Now that's r to the 1 minus k. We have at most n squared over k-term arithmetic progressions, and the probability that each one is monochromatic is only r to the 1 minus k. Even if all of these events are mutually exclusive, the quantity n squared over k times r to the 1 minus k is an upper bound on the probability that some k-term AP is monochromatic. Therefore, when this inequality holds, that namely n squared over k times r to the 1 minus k is less than 1, we'll be guaranteed there exists a good coloring, where by good we mean a coloring in which there are no monochromatic k-term APs. And that inequality holds for n equals r to the power k minus 1 over 2, which is the lower bound we wanted to show. By the way, I think we can get a little bit better bound than this. It seems to me that we can multiply this by something of order about square root of k. And this inequality shown will still hold. Well, that's basically all I wanted to tell you in our very brief overview of the van der Waerden numbers. Maybe I'll just mention, though, that there are a lot of different directions that you can go and generalizations that can be explored. For example, as in the case of our graph Ramsey numbers, we might have separate parameters, k1, k2, up to kr, where each color has its own demand for a length of AP. There's also van der Waerden game based on van der Waerden numbers, where players alternately color the integers from 1 up to n with some supply of colors and look for monochromatic APs. And as a final remark, I'll leave you with, even though this theory is very beautiful, it is fair to say that maybe the determination of specific small van der Waerden numbers is highly computational. You remember that even in our case of w of 2, 3 equal to 9, there were a lot of different cases to check, or at least 2 cases, but then some chasing of colors. Well, this is the kind of thing maybe the computer is very good at, and so I believe the computer is used in a lot of research of specific small parameter van der Waerden numbers, where either coloring is constructed or all possible colorings are analyzed with this sort of forcing method that we looked at. Okay, well, I hope you had fun with this. Thanks again for watching.